So this week, the chapter, the focus is on electric force and electric fields. So just want to give just a very brief overview. Right? So half part of it is on the electric fields, part of it is on electric force. Let me start with electric fields because it's a little bit more um, new and less familiar from you guys. Can you so with after studying this for a week, can you can you explain it to yourself? What is an electric field? Or if someone on the street asks you, can you explain in simple terms, in layman terms, without technical jargons, what is an electric field? I want you to ask yourself that. Right. So Einstein once said that it's credit to Einstein. I don't know if he actually said it, but he said that physics, if you cannot explain a physics concept to an 8-year-old, you don't really understand the subject itself. Okay? So that is a very good idea of when you study. This is a good idea. You try to ask yourself, can I put this in simple language and explain it to someone else? Of course, the technical bits, if you need to calculate the electric field up to 5 decimal places, of course, you need a lot of algebra to train yourself. But to just understand what is it about, what is the concept for, you don't need mathematics, you don't need a lot of algebra training. You should be able to explain what is it for to get an idea. Right? So hopefully in this time you form an answer for yourself. The answer I would give is it's a measurement of how powerful some electric charge is. Or if you think electric charge is also too complicated of work, just how powerful or how influential something is. Okay? How powerful an object is, let's say, electrically. Right? So the only sort of jargon or the only technical term here is electric, but the rest of it, any 8-year-old should be able to understand it. So the only new thing they need to understand is this new phenomenon called electricity that is sort of a new force, and electric field is how powerful it is, right? So the first idea you might ask yourself is, why do I need to introduce something so abstract called an electric field to explain how powerful something is? Why do we need electric field? Why are we making life complicated with introducing a new concept? Can we not do it with force? So it doesn't work. Why it doesn't work is here I was trying to illustrate. If let's say you have a big charge, something that's very electrically charged, and a very tiny small charge. Right? So which one has a larger force? See if you can answer that in your mind. If you couldn't, that's fine, because that is not a complete sentence. Remember, you cannot ask something. You cannot ask what is the force of something. Force is always force on something by something. Okay, so if you just ask what's the force by A, or what's the force by B, that is not a complete sentence. There's no answer. That's grammatically incorrect. So make sure you have force on something by something. So I can ask what's the force on A by B, or what's the force on B by A. It doesn't matter which way you label this as long as you know what you're talking about. So occasionally, the only exception is sometimes you will hear people ask, or a problem in the textbook asks, what's the force on A? What they mean is, what's the force on A by everything else? So you add up everything, right? So that's the only exception. But normally, it's on A by everything. And they're just lazy and they don't write by everything. They just write force on A. All right. So which one is stronger? Is the force on A stronger by B, or is the force on B by A stronger? So this is clearly, B is clearly a more powerful object electrically. However, if you ask the question that I just asked, you don't get anywhere, because these forces are equal by Newton's third law, right? And you can see it if you write out Coulomb's law. It will be Q B Q A divided by the distance between them squared, right? The distance between A and B squared. This guy would be K, and then Q A Q B instead of Q B Q A divided by the distance between them squared. You get exactly the same number. So force is a crappy quantity variable to measure which one is more powerful. Right. So what is the solution? The solution is electric field. So now I'm getting the technical bit, right? So now so how do I just want to know how strong B is. I don't care about A. So the formula here tells me the force between them, but I just need how strong B is. So this solution is divide away QA, right? So if I divide away QA, you see I have KQB over the distance that I'm talking about. So I'm looking at how strong B is at this location, okay? how strong B is at this particular location. So this is the definition of electric field. So maybe I should write it over here. The definition of electric field is the force per unit test charge. So now we can give it a name. This guy, we'll call it a source charge. This guy, we can call it a test charge. If I'm testing how strong B is, I can put in whatever A I like just to so that I can calculate the force between them, but then divide away. However, I don't care about what the charge of A is. I just want to know how strong B is. That's why electric field measures how powerful one object is. And that's why we need this new concept of electric field. So hopefully you can explain, the concept is very simple. The non-technical bit is very simple. You just want to measure how powerful something is. If you want to be a little bit more precise, is how powerful something is at a distance away, at a given location away, right? There's an R in there as well. So you see the formula is over here for a point charge. Now, if it's not a point charge, if it's like a cube or a triangle, it's going to be different. But if it's a point, so technically this is a little bit misleading. Imagine all of this is concentrated in a point. It's just very electrically charged. And so it's KQB over, or KQ source over the distance squared. Right? So it's you see the stronger the Q, the stronger the electric field, and the farther away the distance, the weaker the electric field. And now you need to understand the difference between these three concepts: electric field lines, electric field strength, electric field vector. Make sure you know the subtle difference, not a big deal, but small difference. So if I have a church, you've seen this diagram in the textbook. These are electric field lines. It's telling you if I put a tiny positive test charge, always use a positive charge to test things. This is by convention. You have to pick one, right? So if you put a positive charge here, which way will it go? Well, it will be positive, positive will repel, so it will go this way. So electric field lines are just lines that tell you if you put a tiny positive test charge, which way it will go, right? If this is negative, the little positive test charge would be attracted and all the arrows would reverse. Electric field strength, we basically talk about. This is how you calculate the strength of that electric field. So now you look at this and you see, okay, I have a direction, I have a magnitude. That is precisely what vectors are designed for. So if we're being fancy, we can talk about at every point at this location, I can assign a vector, and we call it electric field vector, such that, so vector has a direction and a magnitude. Right? So the direction is given by the field lines. The magnitude, right, the length of this vector is given by this formula. So these are electric field vectors. The final advice I would give is whenever you have the chance, if you need to calculate net force or net electric field, always try to work with magnitude and direction separately. I would always try to work with, to decide what the direction is first. Notice over here, nothing is in a vector sign. I do not have a, if I put something like this, then I need to put R hat over here. But that, I think usually it's more complicated than, if you want to be very pedantic and technical, then that will work. But usually the easier way to deal with is just decide which way the direction is supposed to point first, and then calculate the strength of that direction. So that summarizes what's the difference between, be careful when you write things like this. When you write F vector, what's the difference? What's the difference between this and this? Remember, the right-hand side is a scalar, the left-hand side is a vector. So when I write the one on the left, this one actually consists of the x component and the y component. The one on the right is just a lazy way of writing this. What is that? Well, that's the magnitude of it, right? So the x component squared and the y component squared. So illustrate that, if I have a vector pointing this way, let's say 3 units this way, 4 units this way. Sorry, it's not to scale. Let's say that. So this is the vector f, or FA, whatever. Sometimes you might have a label. Let's just call it F for now. If this is the vector F, then the vector F is 3 units on the X and 4 units on the Y. Right? Or you can write it like this. And this is called the column form. This is called the component form. I like to write it in column form because it's less work. But yeah, what is F without the vector sign? Without the vector sign, the answer is 5. It's neither 3 or 4, right? So be careful to distinguish having a vector sign and not having a vector sign. So if I have 2 vectors like this, this is, let's say this is 2 units, this is 1 unit, this is F1, F2. If you write in a vector sign, F1 would be 2i. If in a vector sign, F2 is 1 unit and the direction is negative I. Right, negative x direction. If you write in column form, which I usually like better, it's more visual, it's 2 units to the right and 0 units in the y direction, minus 1 unit to the left, right, and 0 units that way. Okay. But what is F1 without the vector sign? Well, that's just the length over here, which is 2. What's f2 without the magnitude, without the vector sign? Just 1, right? Even though it's negative, even though it's minus 1i over here, right? F2 is minus 1i, the magnitude is 1. So what is the net force on at this point, at point P, let's say? Well, the net force at point P, I would deal with the direction magnitude separately. So instead of adding F1 and F2, I would write F1 minus F2. Right? So these are notice no vector signs. So I'm just doing the simple calculation. These could be an x component of something, by the way. Yeah, so I'll deal with the magnitude and direction separately. So the answer is 2 minus 1. It's positive 1. Right? So the final is positive 1. The direction is this way. So that's how I would do it. Although you can work with the full vector. So the net is F2 plus F1, that's 2, 0 plus minus 1, 0, and you get 1, 0. Right? So you can do it this way. I think it's much simpler to look at the diagram that way. All right, that's all my advice I have.